So today our guest is Dr. David Mohaisen from the University of Central Florida. Dr. Mohaisen earned his master's degree and PhD degrees from the University of Minnesota in 2011 and 2012, respectively. He is, like I said, currently an associate professor at the University of Central Florida, where he directs the Security and Analytics Lab. And before joining UCF, he had several different positions in academia and industry. He worked as an assistant professor at the University of Buffalo and research scientist at VeriSign Labs. And after that, he joined UCF. So Aziz, you can start. The stage is yours.
Thank you very much. I appreciate this opportunity that you have given me to talk about my work, mostly the work of my students, PhD students. And so a quick acknowledgement here before I get started. This work is going to be based on a few pieces that already published, and the work was sponsored in part by NSF, NRF, the National Research Foundation of South Korea, and Cyber Florida, which is a local institute, a local organization, and that supports cybersecurity research. So, the main question that we try to address by our research in general, and this particular line of work in particular, is basically the use of machine learning for software analysis and for software security in general. And the question that might come natural is why do we want to have machine learning for software security? And so the answer to that question is that there is an ever-increasing number of bad software or malicious software, malware. So if you look at this diagram here, in the year 2011, there were about 65 million malware samples in the wild. And so this is about the time when I started doing this work on malware analysis upon getting my PhD. And as of the moment of writing those slides, that number increased by more or less 20-fold, so 20x. And so we have today about 1.1 billion malware samples in the wild. So the premise is that identifying malware samples by type is really an important task for security operation. And so you can envision multiple applications that require that kind of identification. And so you might want to filter unwanted malware families like fake AV or ransomware, among others, so that you can focus your efforts in your organization on malicious software that is of interest. You might want to also track some families of interest over time so that you can have some intelligence gathering. For example, if you're interested in espionage kind of malware, then that kind of identification of malware into a type will help you do that. You might also want to use some kind of intelligence for reducing analysis efforts moving forward by eliminating malware that is not of interest. And so how people have been identifying malware samples has been through what we call program analysis, by collecting meaningful features from which that program is analyzed and understood. And so there has been two schools of thoughts on this kind of analysis. There has been static analysis and dynamic analysis. And so for static analysis, what you're looking at basically is going to be a representation of the static or the static code or the program itself, the binary itself. And so there are multiple theoretical tools that you can utilize for such static analysis, including abstract interpretation, data and control flow analysis, model checking, symbolic execution, among others. And so there is another beast that is utilized for this analysis, which is dynamic analysis, and that is by executing the file of the binary on a real or a virtual machine, from which you would collect some artifacts and then use those artifacts to understand the intent of the program. So this is at the abstract level. At the tool level, given that we are engineers and we are really not only interested in theories and just mathematics, but also we are interested in what is the software tool that can be utilized for understanding those systems or the systems of software. And so for static analysis, there are multiple tools, including IDEA Pro. There is Hopper. If you have been working on this analysis, you might be familiar with Hue or HView or ODA. There is also Binary Ninja, which provides you a lot of abstract structures for analysis. Radar 2, which is our analysis tool of choice, given that it is open source, free, and customizable with CLI. There's also Anger, which is part of an effort at the Arizona State University. There's also dynamic analysis tools through which you will be able to execute, maybe in some virtualized environment, your binary code of choice, and then collect some artifacts about that binary code. So there is Cocoa Sandbox, which is our system of choice. There is Bandra. There is Droid Box for Android and Android-like systems. There is Bee Hunter, among many others, as well as something that we have developed in-house for our group, which is called AutoMal. And to exemplify some of the problems that I'm going to talk about, I'm going to explain in a nutshell in the few upcoming slides what is AutoMal. So the problem that you have is that analysis tools really provide output that is difficult to understand and interpret. And I will go over a couple of examples of those outputs. And so conventional analysis is really invisible. So as Gökhan has mentioned, I worked in industry before I come to academia. And so I know for a fact that it would take 10 man-hours per sample to analyze and understand the output of those static or dynamic analysis tools for sample they did not see before. Of course, if you have seen sample, then you would be able quickly to relate to that sample. But for a sample that is fresh out of the box, it will take a long time, 10 hours. And so imagine that you have those 1.1 billion samples, then not all the men on planet Earth would be able to handle that in a day of work. So again, the output itself is not really that easy to digest and analyze. So this is what the output of, say, for example, Radar 2, which is our tool of choice, would look like. You would not be able to tell much other than there are some addresses and a bunch of parameters that are very hard to analyze, even for a small program. Imagine that you have a program that is tens of megabytes. That has great level of dependencies, a great level of libraries. And so, it's really invisible to analyze and understand this kind of code. Moreover, for dynamic analysis, which is a little bit worse in the sense that, you start with some vendor samples or customer samples or internal samples, and then basically you will create a priority list, run them through your system of choice, RML in this case. Then you will be able to fork a VM, use the output of the VM to create some artifacts. Those artifacts would be something like file system and its usage, for example, created, modified, deleted files, or file size distribution, or unique extensions, and the number of files that go under a common path in your system. Or they could be registry, for example, in systems like Windows, which leave some information that can facilitate the execution of files, including keys that have been created or deleted or modified, or the number of keys of certain type. So, typically keys have types. And so, and this is a large body of work that has looked at this kind of modality of analysis, network features. And so when a malware sample is executed, or a program in general has been executed, it will reach out to some endpoints on the internet, on the network, within the local network or the internet, and do some actions. And so you can use those modalities for analysis, dynamic analysis, upon the execution of the file. And that would include, say, for example, IP-related data. So you would have unique IP addresses, ports, etc. You would have connections, TCP, UDP, row. You have request type, what type of request that has been initiated from this endpoint, and response type. Like, for example, if you're talking about HTTP, then response types can be numbers that indicate, how the connection is going. And then size information, including size with the request and the response information associated with this kind of execution of a file, as well as some other critical infrastructure. Because we're talking about endpoints, DNS is maybe the most visible information, but if you're talking about something beyond endpoints, then other protocol-related information can be utilized, including BGP and other routing information like IPF. So you see, the issue here is that, visually, if you, or manually, if you are talking about 2, 3, 4, 5 samples, you'll be able to maybe go over them over a weekend, maybe the whole weekend, 48 hours, you'll be able to digest what is in them. But in a practice, when you have a large number of samples, static analysis and dynamic analysis themselves produce sufficient amount of artifacts, but those artifacts are going to be very difficult to digest. And so machine learning can help in some ways. Here is the output dynamic analysis or the output of static analysis. And what you want to do is that you want to basically get some representation or feature embedding that will be automatically analyzed and maybe mapped to some model. And so that model would be like, a sort of as simple as like, a line in the sand that will tell you like, this is malware or not malware. Could be more sophisticated, and this is going to be the subject of this discussion today. And you will be able to get a label out of that model upon training it in the operation phase. And so this label does not necessarily have to be like, malicious or benign. It could be like, malicious, benign, what type of family of malware. If it is malware, malicious code. I think, Adnan mentioned that one of my PhD students spoke in your school, and he worked on authorship attribution. So, for the same type, if this is like, you have a code and you want to attribute to an author, this is the work that my Mohammed presented at UMASS. It could be a risk score. You can envision, like, say, for example, this code is vulnerable and this vulnerability is of a certain type. So I don't really care about the underlying logic of the vulnerability. I care about this vulnerability has a given risk score. So you can have risk score, you can have related malware, etc. So this is where machine learning can help. So what do we do in my group in this line of work? So we look into some work that looks into what type of modality of analysis that we want to target for our understanding of malware samples based on some, common sense, some criteria of favorability of this kind of modality. We look into also what kind of representation that we want to use for this modality so that the execution of machine learning algorithms would be efficient, and what kind of algorithms that we want to utilize, and then what is the outcome. And then once we have that, we will be able to look into various activities to do with exploring various algorithms in isolation and tandem. We can look into exploring the robustness of those algorithms through analysis against adversarial examples. We can look into as well exploring defenses to the adversarial examples. So this is in a nutshell what I'm going to be talking about. I'm going to talk about exploring some of the analysis modalities we have been employing in our research group, including strings, graphs, and functions. We will look into very quickly into something to do with exploring various ML algorithms in isolation and tandem to understand those modalities upon exploring those, and then exploring robustness through adversarial examples, and then defending against those adversarial examples using some robust defenses. So before I go any further, I want to provide some background. And this background for somebody who wants to work in this space so that you are aware of the challenges that you have to face first. So the first challenge is that machine learning algorithms would typically require you to have some labels. And so, of course, you can go about this problem by envisioning a unsupervised machine learning task. But then, because we are interested in family name, in attribute of malicious benign, this is by design a labeled problem. And so it is very well known in the research community, that it is difficult to obtain good labels for machine learning in general, but for security in particular, because security is oftentimes associated with temporal variables, with intent. The intent itself, it changes over time and over circumstances of the execution of files. So researchers typically rely on VirusTotal for their labeling, and for the rest of this talk, I'm gonna go over like what is VirusTotal and how we use it. But I want you to be very careful about using VirusTotal. There was a study that I did with my colleague Omar Rawi, now at Georgia Tech, was published in Denver 2015, and look at the caveats of employing things like VirusTotal. So this is something that you have to be careful when using that. But what we use for those studies is typically VirusTotal. And so VirusTotal is this engine that aggregates over 70 antivirus scanners and scan engines. It scans files and URLs from various sources of maliciousness, including viruses, trojans, worms, among others, and has different submission methods for URLs, for files. And also has an API for automating the process. The results are typically shared with those who upload them, as well as partners at the back end who actually employ those 70 antivirus scanners. And so it is very useful tool to detect malware and identify some false positives. And the URL for that with the graphical user interface is provided herein. And so the interface would look like this. You can pick what is your submission interface for file, URL search. So uploaded one file, and that file is detected to be malicious. It's one of the malware samples that I'm going to talk about in a second. And so you will have the typical interface. You will have some of those vendors will say that this is a malware sample, and this vendor is listed here. And it's malware sample that is the red color indicate that it is malicious, and then the text associated with the red color is going to indicate what label it has. And so some antivirus scanners would say that I not see this before, and so it is a clean. So this is not real time. This is intelligence database that is utilized to spit out some information about this file, whether it has been seen before or not. Okay. And so there are multiple, useful parts of the system. First of all, there is basic information about the file, including identifying information such as SHA-1 and MD5, still used in this space, or truncated SHA-1 or SHA-256. And then there is the file size. There is the last time that has been analyzed, meaning that it's uploaded before it is logged in system. And so it also has some detection information, like the one that I went over previously. It has some additional information about details or relations or community, like who are the uploaders of this and so forth. So this really provides you some decent amount of information about those files. So again, I'm going to be talking about modalities of analysis. So I want to get rid of this out of the way. What data set we use? So we have our in-house built honeypot that we utilize for basically attracting adversaries to download their payload on our machines. And so out of this honeypot, we were able to obtain, we obtained a large number of IoT malware samples. But for those studies that I'm going to be talking about in a second, we have utilized about 4,000 samples. And then those are divided between 32-bit and 64-bit. About 10% of them are 64-bit, and 90% of them are about 32-bit. And then about 1,100 files of them are invalid samples, meaning that they are obfuscated beyond the kind of analysis that we do through some static analysis that I'm going to talk about in a second. So as a result, we have about 2,900 of those samples that are viable for analysis. And so we look into some of the characteristics of those data items. And so we have various total scan results obtained. The scan date of the dataset was between May 17, 2017 and March 2, 2018. That is for the last time it has appeared. Antivirus software range for the number of scanners that show those samples range between 29 and 61 out of the 70 scanners. And so the median number of scanners is 59 for each sample, and the median for positive detection, that is saying that it is a malware sample, is 28, which is indicative that those samples are fresh and not populated in all antivirus scanners. And so we have a positive detection rate between 0% that it's a malware sample, but none of the scanners say it's a malware sample, because this is something that is presented to us by an adversary, right? Infiltrating our network, our honeypot, and producing it to us. And in this case, we have a positive detection rate of about 67%. About 2/3 of the scanners have said that it is malicious, whereas the 1/3 said it is benign. So again, our honeypot is rich in the sense that it actually has multiple architectures. If you are familiar with IoT design, software design, we know that there is no standard IoT architecture. There is MIPS, ARM. ARM is a large a large chunk of the software and the device hardware design, but it's not the only one as well. So we have raw samples, multiple of those architectures. That is the processor architecture that is the software is compiled for. And so as for this is on one side we have the raw samples that is out of the 4,000 samples that we start with, and then on the other side we have the valid samples. Those are samples that are we can analyze them using our analysis tools. And so if you look here, we have them also not only diverse against the number against architectures that are designed for, but also we have them diverse for the family that we are interested in analyzing, because we're not really only interested in analyzing if it is malicious or benign, but also what type of family it is for. This is part of our design of machine learning algorithms. And so we have samples for Gaffigan, Mirai, Tsunami, Singleton, and so other malware families as well. So As far as analysis tools that we utilize for starting with some insight into what is unique and distinguishing of those malware samples, we use Radar 2. And Radar 2 is our favorite tool of choice because it is easy to automate using Python packages. So it is actually developed in part of it is developed in C, part of it is developed in Python. But the good thing about it is that it actually has both a CLI and API that can be automated from Python. And it is open source, so you don't have to pay for it. And so as far as what kind of analysis we want to do so that we can understand the software, we look into a range of them. We look into string analysis, we look into graph analysis, we look into functional analysis. And so when we talk about string analysis, we talk about anything that appears in the code that has withstood decompilation. When we talk about graph analysis, we are concerned with graphs that are abstracted from the code that can be used as a modality for representation. And so, in software analysis or program analysis, we have both types of dynamic related and static related graphs, including control flow, data flow, or hybrid flow graphs as well. For functional analysis, we look into some functions that appear in the reverse file, and some of the characteristics as well. And so the research question that we try to answer is, well, why are those interesting? Are they capable eventually? Nothing is fancy about the machine learning part of telling you if the code is malicious or benign, if a given premise is satisfied. And that premise is that, do we have a distinguishing set of features across those modalities of analysis? Are those distinguishing features? And so, the question is that, why are those interesting? Are they distinguishing features? And so the issue that we try to address initially by some data analysis is, look at those features and if they are discriminative. And so let's get started. So, the way that Radar 2 would do is that you invoke the Radar 2 over a given file, the way that you do it here, R2 bin list, it will initiate. And so once you pass to it, a program that is, supposedly malicious, it will spit some information. This information will include the strings. The strings are going to be preloaded. And then that's going to be followed by load section, and then followed by dynamic section. And so those are going to be our attributes of analysis. Then you will have some main function, and all the instructions following the main function. Then you will have the registers and associated information, like what is being loaded in the register of strings, of variables, or whatnot that are actually done in the static time, including initiation. So, we start initially with, the first among them is going to be the strings. Okay. And so in the subsequent few slides, I'm going to go over examples just to highlight to you the merit of having this analysis modality. Of course, I'm not going to be able to put for you the 2,900 samples and what they have in them. But if you have to believe what you see, this is a generalizable kind of feature. So the goal here is to understand the malware behavior through strings. And the key premise here, the key intuition, is that strings are the author's hints, authors here, coders, hints to understand their code later on. And so in Radar 2, strings are in the flag section. And so you can see them for example, sort, time, format, color. Those are strings names that you can basically extract from the decompiled file to be able to understand. Now, it's not really only limited to the names of variables. For example, what you can get from strings could be something that may include shell commands. And so a large portion of IoT malware is going to be Linux-based. And so Linux has this beauty of feature that you can employ some of the underlying utilities or system calls to be able to basically unleash the power of Linux for certain functionalities. For example, you can send packets on the network without having to develop the utility itself, right? And so with that, you can basically envision that there would be some shell commands that are being invoked to automate this process. We can also look into, from strings, we can look into the static component of some endpoints, such as IP addresses and port numbers shared with them that are actually included in the string portion of the static analysis. We can also look into special words. Special words could be either names of variables, names of function that withstand the compilation, or they could be, otherwise some special words that can imply maybe the taste of the programmers for naming his variables. So here's what basically one such a string would look like. So and here I'm going to highlight some of the examples I mentioned here about where strings can be used. The first one among them is basically an initiation of remote connection. And so if you look at the first line here, basically bin busybox, this is the equivalent of your bin in Linux systems. And so busybox is a reduced utility of Linux that is limited to only the space that you can have on IoT devices. And so basically here what you are doing is that wget with the option O, and then HTTP, and you pass multiple parameters of choice. And then that is basically what you are doing is that you are remotely connecting to a remote server, obtaining some information, and that information is going to be basically based on what we have here of change the mode is going to be a payload that is a file that is executable, and you are changing its privileges. So this is understood from wget of the IP address using k1.sh, and then the wget with the option. And then after you obtain that, you just basically escalate the permission of the given file that you are actually obtaining and executing, and then you basically upgrade certain parameters. So this all actually is information that is listed in the string portion of your system. And so additionally, also, if you look here closer, you can also find out that we have some drop zones. Drop zones basically are some IP addresses that are explicitly put in the string portion. So basically drop zones are basically IP addresses used for downloading this malicious file or the payload by the adversary, typically used for propagation, and that is going to be put directly in the system, in the software system. You can also envision that, reasonably easily, you can envision that those drop zones or even endpoints in general would be associated with some connection program, like wget can be with FTP or TFTP, with post, with get, if they are like HTTP related functions. So basically, the shell commands can be used to initiate infection of the host. They are part of the life cycle of the malware, and the strings themselves can be used as a capability, as a modality of analysis to track that. All right. So this is something interesting, and this analysis is not really only limited to basically where you are getting this malicious information from, but can also include who you are targeting. For example, one key aspect of malware samples is that you do not only want to basically infect, basically update yourself with the payload, but also you want to infect others. And so you can have targets. And so typically you would have a single drop zone that is infecting multiple targets. And so you can envision that this analysis would actually yield such information. And indeed, we have some study that highlight that. In fact, some of the results from the study are here. So you can basically, some of the intelligence that you can employ from this kind of analysis using endpoints and targets and drop zones is that you can actually find out where are those drop zones, where all those malicious activities coming from, where are those malicious codes are coming from. And so, you can map them to the world and can, try to point fingers where are the sources of those malicious activities. And you can also find out what are the targets, where are the basically endpoints that are being infected by those drop zones. And so one of the insights that we have found out in one of our analysis is that typically drop zones are in very highly connected places, like the US, like Eastern Europe, Western Europe, and the targets are going to be the rest of the world. So and that is not because there is something to do with the US being adversarial. It's just the fact that it's very well connected place. Okay. And so you can also envision that this kind of analysis can give you some intelligence about, the size of the targets or the size of the sources. So you can, have that kind of intelligence map. All right, moving forward, you can also, basically try to find out what is the prevalence of a given vulnerability in a given space. And so you can do that as mapping as well. It provides some intelligence, not particularly for machine learning, it's just for the mining of this modality for analysis. You can also highlight the relationship between drop zones and one another. So you can, for example, the typical system that we could have is that you would have a drop zone that would be associated with a given malware, and then you would have a target. That is not always the case. For example, we know that from news reports, from our own analysis, we know that typically malactors are in competition. Meaning, you hear that a given malactor, a given malware family has been attacking the infrastructure of another malware family. We can also see that kind of dependency through our analysis of strings, indirectly. So we can see that through drop zone chains, where basically what you have is that you have a drop zone associated with a given malware, and then that malware has certain targets trying to infect, and one of those targets could be a drop zone for another malware family. And so you can see that kind of relationship. Why are we interested in this? This is this is distinguishing the initial premise that we have. B, if we are able to identify this with this kind of modality, we will be able to tell something about the ecosystem and the relationship between them, between different malactors in the system. We do further analysis of those chains, and then we can find out the count of them in a given large set. Among that we analyze, we found chains of length 2, something like the one that we have here. There are 35 of them. Length 3, there are 10 of them, and so forth. What else can we say from strings? Okay, so IP addresses are one thing, shell commands are one thing, endpoints are one thing. Can we tell us more? Well, there are those special words, right? Special words may include, basically, again, by now you should have that feel that we can actually have information about, being able to track the life cycle of the malware. But also there are some, special words. Particularly in IoT malware, we were able to see clearly that there is an extensive use of cuss words in the naming of the utilities. This in itself might not be interesting, but it is distinguishing. Okay. Again, removing traces. Typically with automation, we would not see that kind of capability. But given the type of life cycle that you have with malware, we can see some indicators of removing traces, which is in itself distinguishing. Okay, so this is as far as strings. What else that we can see? And here I'm going to try to go fast so that we can have some time for the actual machine learning and the robustness analysis. So graphs, again, if you're not familiar with what the graphs that we're talking about, here we're talking about something like CFG, so block level CFG. And so one of the nice features about Radar 2 is that once you load the program, then you can get a representation, abstract representation of that program at the block level. So it will give you for example, this is a block, could be a function, and that function calls another function, calls two functions, a couple of them, and then those actually are connected to another function and so forth. So you can imagine that nodes in that graph are going to be blocks, could be functions. Again, here I'm not really trying to be all inclusive, because that block could be also an instruction, could be as simple as a statement, could be a function as well. So let's stick to the idea of block. And so you can envision those blocks as nodes, and then the call among those blocks is going to be basically the edges between those nodes. Okay, and so any program will have unique representation in a way that captures this kind of call relationship. Okay, where nodes are going to be blocks, and relationships between them, edges between them, are going to be the calls between those blocks. So what do we have with respect to this kind of representation for the different data sets, for the data set that we had for the different architectures? So here on one side, we have the architecture that we had, and then total malware samples that we had for each. And on one side, we have some characteristics of the graphs resulting from the analysis of those malware samples belonging to the given architecture. So what do we have is going to be the average number of nodes in the given graph. So you have, like, say, for example, for ARM, we had 665 malware samples. Once we extract the graph, the control flow graph for for each of the samples, the average number of nodes, and by the way, 99.55 means that those are the samples that we were able to obtain a graph for. It's an overwhelming majority, and so each of the, like, on average, each of those samples had 64.13 nodes, and so on average also had 96.66 edges on average. We had also the average shortest path. You can envision that between each node there is a shortest path, and then the average among them for all the pairwise shortest path. And then the average, basically, D stands for average density. And density is calculated as the number of edges for a given node, like that is the degree of the node, over total number of nodes in the graph. So one thing I want to just highlight quickly from this analysis, I'm not going to bore you with, like, all of it, but let's pick something random from here, like, say ARM, and let's say x86. I want to look at those four columns here. Column 4, 5, 6, and 7. That is the average number of nodes, number of edges, number SP, and then D. And so if you look at, like, for example, x85 and ARM, okay, x85 and ARM. So you can see that even as a simple representation of a feature, 53 is clearly different from 64, right? And then 78 is clearly different from 96. And 7.86 is clearly different from 8.89. And so 0.02 is clearly different, not clearly different. It's not different. It's the same as that of the above. But if you look at the different features here, you'll find that in simple terms, there are some discriminative features to be able to tell which architecture it is. The hope is that we will be able to obtain some features that can tell us if it is malicious or benign, or which particular malicious code it is, which family it is. Okay. So that is as far as the graphs, and I'm gonna, like, again, this is just the brief intuition. I'm gonna go quickly over some other static analysis features for the graphs in subsequent slides. And again, the slides are going to be shared with Dr. Cole, so he can share it with you, later on, if you're interested in looking into those features. So we look also in function analysis, function types. There are, like, libraries, that is GNU standard libraries, and there are some non-standard or custom functions defined by their users. 7% of the samples do not have a main function, and as a simple principle, in order to be able to conduct any static analysis, you have to start with a place that is going to give you some good coverage, and that a place typically is the main. So you start with the main, and then you execute the main, and then you can branch into, like, say, for example, the graph of choice. So what we do actually to resolve this problem is to compare CFGs generated from some codes that have the main function, compare them to those candidates that do not have a main function, and then we just, like, with the plausibility, we can tell that the main function is this particular candidate. So we look into, for example, an example of, like, where this main function does not exist. You see, like, at this instruction, there is a branch, and then the branch just, like, starts, and then you have, like, multiple possibilities for main function. One of them could be, like, something that is just right after the branch. Could be, like, one among many candidates. This, by the way, like, this approach, turns out to be quite successful in estimating those malware samples without main, estimating the main for those without main. Let me go very quickly over those. So again, those are just features of discriminative features of malware samples without main, with no data section, with no load, etc. So this is just a characterization of them. I don't want to bore you with the numbers. I want to go to the machine learning component of this as well. There's, like, the number of samples across architectures with drop zones, with target IBs, which the ones that had target IBs in them. And then the percentage of those that had the target IBs, the ones that had shell commands among the features that we analyzed, the ones that were obfuscated, and the ones that had obfuscated functions as well, they are listed. We also conduct this analysis not only for the architecture, we look at for the malware family, across the malware family, again, for no main and no data, among others. And as well, we look into what constitute reverse successfully, and malware samples with the cross architecture, CA, malware samples with the graph that is resulted. So this is just among those modalities that we have analyzed, how many of the samples had that modality of analysis. And why this is important, this is coverage. If the modality itself is not good enough to capture all malware samples, then that's not good modality. We also looked into over families, and then how basically they have how those families correspond to the use of certain protocols of UDP, TCP, HTTP, or if they have cross architecture, or if they have a graph. And so, for example, for Gaffigate, you find that about 100% of the samples had actually a graph in them, meaning graph is a good candidate for analysis. So, what is the machine learning component? Starting with this analysis, now we have some intuition that those are meaningful features of analysis. We want to get some good representation of those features that once we train a model with them, we'll be able to tell if a given code is malicious or benign, or if it is malicious, what kind of maliciousness it is. And so let's get started. We start with a sample, and then we can get multiple types of features, such as metadata, some basic information about the malware, including the size and size of sections. We can extract graphs the way that we discussed earlier, with some features on the graph. We can look into functions, and then some features from the functions, and then some flag information, and some feature on those flag information. And then we can look into reducing those features into something that you can manage. For example, one of the things that we have looked into, if you look into basically some basic information about the contents of the file as hexagrams, 1 gram, 2 gram, 3 gram, there's going to be a huge number of features, in the order of tens or hundreds of thousands of features. You cannot really run this in a feasible way into your machine learning algorithms. So basically, you need to run that into some feature selection algorithm that would look into using some model or some baseline would give you basically the set of features that are most discriminative. A limited number of them that is most discriminative. And then you would run them into your classifier of choice, and then you would basically able to get some results for the training part, including AR, accuracy, false positive, false negative, and then you will be able to tune your system. And then another batch, you'll run it for something that you do not know, a malware samples without a label, and then you'll be able to use the output label as your label of choice for the sample. This is a general framework. So what kind of algorithms that we use? So we use both shallow learning and deep learning algorithms. So for an example of a deep learning algorithm, and I'm going to talk about those in a second, we'll talk about graph-based approaches. But for for deep learning algorithms, MLP is one of the things that we have used. You start with some feature representation. The feature representation is going to be all of those features that we mentioned, whether they are the output of some feature reduction or just the raw features. And then that's going to constitute the input layer. Then some parameters are going to be adjusted based on some back propagation criteria for the given labels. And then you will have an output layer. The output layer could be just benign or malicious. In the case of detection, they could be the given family name if it is about classification. Another approach that we utilize heavily is random forest. And so random forest basically is that you start with a bootstrapping of samples, and then you have a decision tree across the features grown to the fullest size. And so you have multiple trees, tree 1 up to tree n, and then you can vote on the outcomes of the trees to be able to tell if it is malicious or benign. The same approach can be applied to tell if it is malicious of a given type. So what do we have of results here very quickly? So again, I'm gonna go into more details of individual classifiers. This is in tandem, including the metadata, including graphs, including functions, flags, and overall. And so what we have here of MLP, overall, you will be able to achieve all of those. Actually achieve above 95% of an accuracy rate, which is quite promising. Okay. And overall, you have over 96.9% accuracy. You might be asking well, if MLP is able to achieve individually higher accuracy, then what is the point, for individual ones, what is the point of trying multiple of them? The idea is very simple, is that we have seen that some actually samples do not generate a graph. For those, you will be able to see them in the data, but the data itself can be still obtained. Or in case you're not able to obtain the graph for any reason, flags are still accessible. So having multiple approaches will give you multiple opportunities for the analysis and detection. Similar results are obtained for RF, random forest. And so, looking at the most distinguishing features, those are the number of features, like the number of times the feature occurred for, say, given strings. And so, you can see that those strings are particularly. So this is the number of them, and then the number of the strings and the frequency. And so you find that they are diverse in a sense. So they're not like say a derivative of the same word. All right. Is this the only modality that we can utilize, like those modalities? Of course, you can go about representing modalities in so many ways. For example, you can look into system calls, right? So not only graphs, but individual calls, that path in a given graph. And so here is a malicious API call sequence, and here is a benign API call sequence. You'll find that if you represent those API sequence calls into some graph representation, you will find that the malicious one actually looks at, structurally looks quite different from that of the benign one. The benign one will have a certain complex structure, whereas the benign one, whereas the malicious one would have actually a structure that is only triggered with an if-else kind of statement. Okay. So you can utilize that as well. Okay, so again, for graphs, you can also see that those features are not only capable of distinguishing between malicious IoT and benign IoT, they can be also utilized for telling platforms apart. For example, for edges, you can use a number of edges, a number of nodes to tell if a given malicious code is an Android code or IoT code. You can also use density. You can also use the number of components in the given graph. And so, for this particular graph, we see that the Android system has, with respect to the CFG, has a large number of components compared to one component in the IoT system. And so you can generalize for other features, including average closeness, average betweenness. You can look into radius, diameters. You can look into average degree centrality, shortest path. All of those are very unique features. And so again, I don't want to bore you with this, but you can envision a system that can tell you IoT benign, IoT malware, or Android malware, if that is of interest. And so the way that you would do it is that you would go through, and it's assembler, find the main. If the main is there, then use it to extract the CFG. If it's not there, then approximate it, and then you can have all of those features condensed together. So you extract those features from general features, and then you can conduct the detection. I'll talk about a generic detection architecture in a second, and then you can establish your evaluation metrics. Once you are comfortable with the accuracy that you have, then you can run that through for learning. A typical architecture that we heavily use include convolutional, multi-layer convolutional networks to be able to slice and dice the features in a way that would be representative. And I think Mohammed, when he spoke in your school, he spoke about his CCS paper where he developed this deep learning neural network architecture that is capable of getting a high quality representation of features for authorship. We use the same thing here for malware. And so, not the same thing. I mean, in the same line, we use different architecture. He was using DNN. Here we are using CNN with multiple layers. And so, again, I'm going to skip over this. I think I'm going to go over time anyway. So, once you are happy with the accuracy of the choice, then you can actually run this for the learning component. So, what do we have of results? We have results for both the detection and the family-based classification that reaches up to 99% in both cases for accuracy, and has some very promising results with respect to the false negative rate, false positive rate, the false discovery rate, and the false omission rate, FDR and FOR. Now, one thing to keep in mind is that we tried all other approaches like non-deep learning systems or algorithms, but of choice is CNN. All right. So, okay, so let me shift gear very quickly and just tell you a little bit about another piece that we have conducted that looks into. So far, what we have been building is things that are constructive, that are meaningful. That you start with a code, you get some features from that code, representative features that are discriminative, and use them for telling that the code is malicious or benign. Or in a better case, you can tell if they are particularly not only that, but like what family they are. So here, what we look into is how to break that kind of classifier. The idea is quite simple. Let me see the chat. So, all right. So, the the idea is very simple. So you start with building the classifier, and you have eventually you start with, like, say for example, some training data with samples and labels. Disassemble them, get the features, CFG features, and then extract the features, and then you have those graph features, feed them in the classifier, and then that classifier will give you a model, and that model will give you some accuracy. Then for testing, you do the same thing. You meet that accuracy. Now for the adversarial examples, what you do is that given that feature X that you have, that you start with, this feature obtained from here, right, from the graph features, you can add some noise on top of that feature in a way that will give you another feature that is distorted, that you can validate, and that feature will give you a different label than intended. Very simple, right? In a second, I will tell you that it's not really a good idea. So we tried this actually with some, again, some caveats. You apply minimal perturbation, and then you preserve some illegal values. For example, you do not expect, say, a degree to be -5. Degree is going to be like positive value. And so we tried 8 off-the-shelf adversarial example techniques, and then we were able to fool the classifier. Why this is a bad idea? It's a bad idea because actually changing one value in the original feature is not independent of other values. For example, the shortest path depends on the number of nodes that you have in the graph, the number of edges, etc. So when you change the number of edges, there's no guarantee that it's going to be the shortest path anymore. So an adversarial example has to start at the graph level. And so what we want to do is basically start with some selected sample, and then you want to basically inject this sample in a target so that you can get a graph that manifests the feature of choice. Okay, so start again with, say for example, an original graph, original function code, and then that function itself is going to be combined with another function of selective choice, and then eventually you'll have that longer code, which is typically what we do with code injection in code design. And so you will have basically this is the original, is going to be blocked, and this is the target, the blocked, and if you have a single code. And so basically the graph is going to be original given, and then selected given, and then the resulting file is going to be a combination of both. And that is basically what we have. Basically what we have is basically a graph that is the result of the combination. So this is what we called graph embedding and augmentation, GEA. This work was published in ICDCS 2019. And so again, you can execute this kind of simple idea. You can actually see how it can fool the classifiers. And so we can fool the classifiers in multiple ways: targeted, non-targeted. For example, we can basically make a malicious code looks like benign with respect to the classifier. And so with the minimum number of changes, we were able to basically achieve a misclassification rate of 7.67% with adding only 2 nodes. By adding a maximum of 455 nodes, we were able to achieve 100% misclassification. And with a median 24 nodes adding, we were able to achieve 95% of misclassification. Misclassification means that something that you start with as a malware will become benign, misclassified into benign. So this is in a way a success rate for the adversarial example. And so with the increase of MR, you would expect that the crafting time is going to increase. That is why, you have here with that order. Again, not only malicious to benign, you can also convert benign to malicious, and with a similar success rate. Although it's more difficult to convert benign to malicious, it's easier to convert malicious to benign. Again, I'm not going to bore you with the results. I think I'm going to go over time. Let me go over this final piece upon which I'm going to conclude, and that piece is to look into detecting adversarial examples. So now we have seen that you were able to classify, you were able to fool a classifier. Now I want to be able to detect that an example X prime that has been manipulated to fool the classifier. And so the idea that we have with the GIA is that you start with original CFG and target CFG, and you combine them. Okay, I wanted to detect that combination. So the idea is that you start with a feature extraction algorithm, and let me go back. So you start with a feature extraction algorithm, and then you have the basically adversarial example detector, and that would look into, is that AE or not. If it is AE, then basically adversarial example, do not process it. If it's not AE, then just you extract the features and classify it. And so as for the this component that looks into whether it is AE or not, basically you look into this assembler, generate CFG, then label it, random walk on it, and grams on it, and feature representation is going to be your feature representation. So how to detect actually the examples? We start with two ideas for detectors. The first idea is basically to conduct randomization of the feature. And so to be able to randomize the features, you have to have labels on top of the graph. And so the idea of labeling here, we use two ideas. One of them is density based, and one of them is level based. So for density based, what we do is that you start with by scoring each node based on the summation of the in out degree over total number of edges. So this is basically density, typical density. And so the most dense node is going to be labeled as 0, and the least is going to be labeled as n. And so in this case here with DBL labeling, you'll find that 0 here, because as we can see here, this is the highest degree. It's going to be 1, 2, 3, 4 over the number of them is going to be 0.4, I believe, or less than that, 0.36. And so this is the highest. The second one is again 1. In the case of these, actually, if you look at them, they are actually the same number, 1, 2. The way that we break a tie is that you look into centrality factor, and if one with the high centrality, you give it the lowest label. If they are the same, then you just break it randomly. So this is one way to start. Another way to start is to do level based labeling. And so the node with the highest label in a breadth first search is going to be with the highest label. The one with the lowest is going to be with the lowest label. And again, for breaking tie, use the same thing. So the idea for detecting adversarial examples is to start with a random walk approach with random steps, basically convert the graph undirected, and then basically repeat the random walk X number of times, so that you have a set of basically sequences from the random walk, and use those as your features. You can use them as n-grams, basically. So the n-grams then are run over on top of the random walks that you have obtained. So we use once you have the n-grams, then we use basically the top features among the n-grams obtained from random walks, and then for our experiments we use 500 discriminated features from LPL and DBL each, and that gives us 1,000 features. So what do we have of feature representation here? So when we train test and the total, the percentage of the benign were 17.94, Gaffigate is 66.18, and then Mirai is 14, and then Tsunami is 1%. Okay. So the detector, how the detector works. So this is as far as the initial classifier. How does it work? So the detector itself is an autoencoder with input layer of 10 1D input vectors of basically 1 by the number of features that we have from the random walks. Hidden layers eliminate the feature dependency. Output layer with 10 1D vectors of size 1 by 100. And then validation unit to output basically the RMSE. And then if the RMSE, basically what we use here is you pass everything through your encoder, and you pre-train an encoder, And then for each potential input, that could be a malicious, like it could be an adversarial example, you basically calculate the RMSE, and if the RMSE is above a threshold, in this case we use 50% or 0.5, then consider it as a malicious, as adversarial example, otherwise leave it in. The idea here is that your initial encoder is built based on some features that are close to one another. Those are selected features. So if your RMSE, error in your feature for the given example is high, it means that it's manipulated. Okay, so for classifier, we use again CNN with the same size of features, and then we use 3 blocks of 2 convolutional blocks and a classifier block. Here are the results. So for benign, the baseline, we have the number of them that are detected are 85%, 85 point some percent. For Gaffigate, we have 99.5% overall. And then for Mirai, for the large, again, 93.67%. And overall the average, this is a macro average, is 97.79%. Something to notice that, it's not always possible to detect all kind of examples, adversarial examples. Again, in the previous experiments, I showed that it's difficult to actually generate adversarial examples for benign, converting benign to malicious. And again, here, it is very difficult to actually detect those conversions, like, in this case, 85.34%. Why it works, I want to skip this one to conclude. Again, I think I went over time by too much. So in conclusion, software really provides you a great set of modalities for analysis. Examining those modalities is a cumbersome, and so machine learning can help in automation. ML itself is prone to adversarial examples, and we have demonstrated that. And so defending against adversarial examples is an open question. And we have provided one such approach with randomization, but that is opens a lot of doors for improvements, including encoding, compression, squeezing, among others. There are a few papers in this space that we have published over the last couple of years. And so here is a list of some representative papers. And so with this, I would be very happy to answer any questions if you have.